This presentation introduces the concepts and equipment used in underbalanced drilling operations. The key differences between underbalanced drilling and conventional overbalanced drilling are at both the conceptual and the technical level. At the conceptual level, the subsurface drilling conditions need to be investigated further. The rotating drill bit cuts away rock to deepen the well. The drilled cuttings are lifted to the surface by the circulating drilling fluid. In conventional overbalanced drilling operations, the hydrostatic pressure exerted by the drilling fluid in the well is designed to exceed the pressure of the hydrocarbon fluids in the reservoir. Since the pressure in the hole is higher than the pressure in the rock, fluid and fines are lost to the formation. These losses cause damage to the near wellbore area, resulting in reduced production. Experience shows that even a short exposure to overbalanced conditions can severely impair the productivity of a well. In underbalanced drilling operations, the hydrostatic head of the drilling fluid is designed to be less than the reservoir pressure. This means that there's a continuous flow of hydrocarbons into the well during the drilling process. Under these conditions, no near wellbore damage occurs and the well's ultimate production is not impaired. The prevention of wellbore damage has several advantages. Near wellbore damage prevention is just one of the benefits of underbalanced drilling. Another benefit of underbalanced drilling is the reduction of drilling problems, such as differential sticking and drilling fluid losses. Producing the well while drilling increases reservoir knowledge. With this knowledge, wells can be steered into more productive zones. Reservoir pressure and depth determine the required density of the drilling fluid system. Unlike conventional drilling, which is limited to simple fluid systems, underbalanced drilling uses a variety of fluids to control bottom hole pressure. At the high end of the density scale, light fluids such as water, synthetic base oil, natural crude or diesel form the drilling fluid. To achieve lower bottom hole pressures, a two-phase flow system can be employed. This system consists of a light fluid aerated with a gas, such as nitrogen or natural gas. Foam systems generally consist of water and a surfactant. At the low end of the scale, mist or air-based systems can be employed. Each of these fluid systems requires a different surface setup. In what follows, the commonly used two-phase flow system is shown as an example to illustrate the technical differences between underbalanced and conventional overbalanced drilling. A two-phase flow system setup consists of the following elements. The light drilling fluid is stored in the rig's mud tank system and is pumped to the well by the rig fluid pumps. Lifting gas, in this example nitrogen, is injected into the fluid stream. Depending on the quantity of nitrogen needed, the source of the gas can be cryogenic tanks or a membrane unit that separates nitrogen from the air. The two-phase fluid stream is injected into the drill string using the conventional rig systems. The two-phase fluid exits the bit at the bottom of the hole, carrying drilled cuttings up the annulus. Since the hole is drilled underbalanced, reservoir fluids such as oil or gas are produced from the reservoir and mingle with the two-phase fluid moving up the annulus. This means that the well is producing while being drilled. The return fluid from the well is diverted by a rotating control head to the surface separation equipment. The control head seals around the drill pipe while allowing the pipe to move in and out of the well and rotate. In some cases, a snubbing unit needs to be installed to allow movement of the drill pipe in and out of the well under pressure. Moving slips on the snubbing unit grip the pipe and push or pull it against the upward force in a controlled manner. Flow from the well is controlled via a choke manifold and then processed in a 4-phase separation system. This system separates the returns into its constituents: light fluid, crude oil, nitrogen and natural gas, and rock cuttings. The separated cuttings are collected for disposal. The separated hydrocarbons are sent on to production facilities or flared. The light fluid is pumped back to the rig's mud system for treatment and reuse. This completes the tour of the main surface systems that are used in 2-phase underbalanced drilling operations. In summary, underbalanced drilling allows the well to produce during the drilling phase. Underbalanced operations require additional surface equipment and a careful upfront design. When applied in appropriate wells, underbalanced drilling prevents formation damage, reduces drilling problems, and increases reservoir knowledge.
It's no secret that the solution to the rising demand for natural gas supply in the United States lies in the ability to economically develop unconventional gas resources, especially coal bed methane and shale gas. Coal bed methane accumulations in the United States are estimated to total more than 700 trillion cubic feet and as much as 7,500 trillion cubic feet worldwide. With both environmental sensitivities and North America's natural gas consumption on the rise, the question is how to recover this huge methane resource in the most efficient and cost-effective manner with a minimal environmental footprint. The answer lies in the patented underbalanced multilateral drilling process that eliminates the possibility of formation damage and creates greater reservoir exposure and aerial sweep within the formation. The process can be termed a mechanical fracturing technique. By combining multilateral drilling with a system that combines gas production, dewatering, and disposal all in a single well, we eliminate a large part of infrastructure, long-term maintenance, and environmental impact associated with vertical well systems. The radial network of boreholes allows for a faster production of formation water due to greater and more precise access to coal seams, without damaging the formation and with a reduced environmental surface disturbance. In fact, with this system, a single well can produce as much as 8 traditional vertical wells on 80-acre spacings, significantly lowering drilling and production cost, while at the same time increasing recovery rates. Elimination of formation damage is achieved by utilizing underbalanced drilling with a dual injection annulus system that isolates the damaging drilling fluids away from the formation. Higher recovery rates are due to greater aerial sweep, precise placement of boreholes within the coal seams, and the complete elimination of formation damage created during the drilling process. The end result is significant cost reductions and higher yields of methane gas in a shorter time period, all of which adds up to increased net present value of the property. This system has the added advantage of providing access to coal deposits below 5,000 feet, which are estimated to hold more than 50% of the gas reserves in many major coal bed methane gas regions. Virtually every environmental concern about hydraulic fracturing raised in both the Bingaman Bill and Leaf versus EPA are solved by this process. We begin the process by drilling a deviated wellbore to a joint just above the productive coal seams. Casing is set and cemented into place. We then drill a pilot well through the productive coal seam, and the wellbore is extended for 100 feet below the deepest coal seams to be accessed. This extra 100 feet serves as a sump area for collection and disposal of produced formation water. The drilling assembly is then extracted from the wellbore, and we are ready to begin drilling the underbalanced multilateral wells in the coal seams. We lower the upstock into the wellbore on the end of a 7-inch casing, which we call a carrier string. Unlike other retrievable whipstocks, which are lowered into the well and supported on the bottom by a packer, this proprietary upstock is run into the well on casing and hung in the wellhead, thus creating a dual injection annulus necessary for underbalanced drilling. The upstock is placed adjacent to the first coal seam and oriented in the proper direction. At this point, we lower the multilateral drilling assembly into the 7-inch casing string down to the upstock. The drilling assembly is then oriented in the same direction as the upstock. We now begin the underbalanced drilling by pumping fluid down the drill assembly to the activated mud motor and guidance system. The dual annulus prevents the damaging drilling fluids from coming into contact with the formation. While the drilling fluid is being pumped down the drill pipe, air is pumped down the microannulus. The drilling fluid and the air meet at the upstock and rise up the return annulus inside the carrier string as commingled air and drilling fluid. This process allows for formations to be drilled as low as 2 pounds per gallon equivalent circulating density. ECDs can be adjusted as borehole stability models dictate. As much as 7,000 feet of multilateral wellbore can be placed in each individual seam. Upon completion of drilling the first coal seam, the motor assembly is retrieved to surface, and the upstock is now ready to be moved to the second coal seam location. The upstock does not need to be retrieved. We simply add joints of casing to the carrier string, lower it to the next zone, and orient it. The process can be repeated for as many as 10 laterals without having to be retrieved. Upon completion of the last lateral, the upstock is then lowered to the bottom of the sump area. During the drilling process, we placed in the 7-inch carrier string an annulus casing packer. The function of this packer during the completion phase is to isolate the annulus between the 9 5/8 casing and the 7-inch carrier string. Once the upstock and carrier string are in place in the sump area and sealed in the wellhead, the annulus casing packer, now located just above the 9 5/8 shoe, is inflated and pressure tested for competent seal. A perforating gun is then lowered on a wire line into the carrier string to a point just below the 9 5/8 casing shoe. The gun is activated to perforate the 7-inch casing. The perforation gun is then retrieved from the carrier string. An electric submersible pump is now lowered into the carrier string on tubing. The ESP is spaced in the carrier string near the bottom of the sump and secured and sealed on the surface. The water is now pumped to surface inside the tubing. After the coal seam begins to dewater, methane gas is released. The gas migrates up and enters the 7-inch casing through the perforations and is pumped to surface via compression. If the formation water is suitable for use, this process is complete. If the water has high salinity and needs to be re-injected, 2 options are available at this point. If the water injection zone is in a formation above the 9 5/8 casing shoe, then the water is returned to surface, can be pumped back to the outer annulus between the 9 5/8 and 7-inch casings and forced into a suitable water injection zone through perforations at any point in the casing. If above coal seam injection is not feasible, then the ESP can force the water into the zone adjacent to the sump area. This injection system can handle both the produced water generated from its own production as well as produced water from other wells. As you can see, this patented process combines production, dewatering, and disposal operations in a single well. The result is minimal environmental impact, significant cost reductions, and higher yield. And we are ready to begin drilling the underbalanced multilateral wells in the coal seams. We lower the upstock into the wellbore on the end of a 7-inch casing, which we call a carrier string. Unlike other retrievable whipstocks, which are lowered into the well and supported on the bottom by a packer, this proprietary upstock is run into the well on casing and hung in the wellhead, thus creating a dual injection annulus necessary for underbalanced drilling. The upstock is placed adjacent to the first coal seam and oriented in the proper direction. At this point, we lower the multilateral drilling assembly into the 7-inch casing string down to the